Morning, everybody. We are Siligram, and we've created a weight measurement tool specifically designed for silicone wafers. My name is Isaac. This is James, Dante, Tommy, and Jackson. Texas Instruments has tasked us to create a weight measurement tool that detects defective silicone wafers. Our tool measures the mass before and after a very thin layer of copper is removed from the wafers, and this measurement is taken to ensure that the wafers are not defective. James is going to talk to you about some of the requirements of our project.
Thanks, Isaac. So, our solution is going to support 200 millimeter wafers, and it has to test at least 60 wafers per hour. Each of these tests need to have a range of about -1 to 1 milligram per wafer, as away from its actual value, which comes out to be about 0.16 milligrams of standard deviation at 6 sigmas of confidence. Furthermore, the repeatability of this test is also about 1 milligram. So that means a 200 milligram weight today would weigh maybe 199 milligrams to 201 milligrams the next day. And finally, I believe we needed to incorporate this into TI system, so figuring out a way to interact with the overall system, in TI's process. I'm going to pass it over to Dante to tell you more about how we achieve this.
Thank you. So we split up the hardware into two main subsystems, the first one being the weigh cell, as you can see in the middle picture at the bottom. Also in the bottom picture on the right, you can see kind of the technology that's going on inside of it. It uses electromagnetic force restoration technology so that when an object is placed on top of the chuck, with internal systems, it equalizes out and then outputs both to a display unit as well as a PC via RS-232 serial data bus. So that was the first half of actually getting a measurement. The other half, is our environment control. As you can see in the top right, we custom designed an enclosure with item 24. We have 5 polycarbonate panels and a 1/4-inch aluminum base that the weigh cell is mounted to try to equalize, level out, and create the best environmental conditions. Additionally to that, we do have a door that's operated by a linear actuator to prevent wind drafts when the measurements are being taken. I'm going to pass it over to Tommy to talk about our software implementation.
Thanks, Dante. Our system is controlled by a Python script that handles 3 main subsystems, which is opening the door to allow for an end effector to come in, communication with TI systems so that we know when and where a robot is to hand off wafers, as well as pulling the data from the weigh cell itself. This is done through an RS-232 protocol. All these are timed internally so that we don't have anything crossing over. We're not trying to place a wafer when one's already inside the machine, and we're not trying to pull data when there isn't one on for us to weigh. I'm going to let Jackson close out here.
Thank you, Tommy. So then in conclusion, after many hours over many days of testing both here in-house at UTD and also at TI's fab, we've been able to achieve an accuracy of 0.1 milligrams with a standard deviation of 0.15 milligrams, which is below our requirements for the project. And we've also been able to incorporate compatibility with 300 millimeter wafers, which is a stretch goal, as the original goal was 200 millimeter wafers. Thank you very much.
Is 0.1 milligrams this your accuracy or resolution?
0.1 milligrams is actually the resolution of the scale we have. And accuracy, do you mean precision or accuracy?
Similar things, right?
Well, precision is, never mind. Yeah, precision is how far you are, how grouped your data is. Accuracy is if you got the data. So for our precision, we do have a standard deviation of 0.15 milligrams, right? Which is about what we should expect. But again, this weigh cell is actually meant to be as accurate to 0.12 milligrams, as precise to 0.12 milligrams. And so there's definitely room to improve with this system.
What sort of defects were you trying to find? I mean, is it like bits are broken off? Or?
So this picture down here on the left side, that column on the left is a group of good wafers. The group on the right is a group of bad wafers, and those are copper vias. They're like wires running across the silicone wafer, and so when that via gets too thin and high current is running through it, it starts to peel off. And so the reason that it's getting over etched is because they have to use a wet chemical etch to remove the underbump metallization, which provides something for the copper to stick to. And so they have to use a wet chemical etch because it's copper and they have to remove a lot of material.
So what happens when you detect one that's over-etched?
It's
It's the board is bad.
Yeah.
so
So-
scrapped.
This is a
Is
fault
it-
detection, not fault prevention.
Is there an automated step that throws the wafer out?
Well, no,
we,
so
we didn't build anything of the sort. No, we would be able to report it to TI's database. All of our data is put into TI's database, and they would be able to go and look at that and see that something's lost.
And it's organized per lot, per wafer group, so like 25, and then you can see exactly which weight corresponds with which wafer. So you can, I guess, narrow down to which wafer it was and then take it out of your production.
The wafers are measured before and after etch?
yes.
Correct.
So our system doesn't actually do the deviation because then we would have to have a memory system, right?
Right.
So what
we
we do
just output to TI's database.
Yeah.
So what limits your throughput?
Did you discover the need for the enclosure during the project, that air movement caused problems, or did you have that?
Immensely.
Yeah, the
Right.
surface area of a wafer means that even if there's a slight breeze, you're going to have wild fluctuations in your weights.
So initially we wanted a system without a door because it's much simpler. But when we did that, we realized whatever minute air currents that would flow through that door would create a lot of movement on its weight, especially down to the 0.1 to the milligram accuracy. That's why we did include the door.
So what limits your throughput to 120 wafers per hour? Why can't you go to like 200 or 300?
Mainly stability time. It does require anywhere from 10 to 20 seconds for all of the environmental conditions to completely stabilize in order to get an accurate result. And we do our own statistical as well as the filtering of the waste cell itself, kind of analysis, so we make sure we get a repeatable result to the best degree that we can.
Furthermore, we have to average most of the readings because that's actually how the cell does that too, right? It takes readings and it averages them. We let it stabilize such that we know that it's constant for 3 seconds before we take the reading. So that way we are sure that that's what it's actually reading.
Can you guys tell me the enclosure, is that filtered? Because if you have dust on a wafer, that can affect the weight of it.
Yep.
For
How
sure.
small it is, but it can. So is that a filtered enclosure or not?
This will be placed inside of a clean room, ideally, so we wouldn't need to worry about filtering ourselves.
Okay. All
You
right.
collected statistics about the variation of the delta weight per etch wafer per lot or across different lots?
Right, so with our system we can do that, but again, TI didn't give us all their wafers to do this, right? They gave us test wafers that they know were bad. They didn't give us any good ones. So we can't say, oh, now we know this data, because the good ones they're selling. Yeah.
All right, let's thank the group.